both as a wave and as a particle at the same. Okay. When we're talking about electronic configurations of different elements, okay. So far we were talking about like the mole concept. We were talking about the particulate nature of matter. Okay. We were talking about how matter behaves as a particle. Okay. Now, when we want to discuss about electronic configurations, or especially when we want to describe um, our matter in terms of energy, okay, in terms of energy, very important, then wave we can describe it as waves much more easily. Okay. So the wave form of matter is more useful to figure out energy calculations, or to figure out how energy behaves in matter. Okay. All right. In particulate nature, it's more to quantify, okay, the particle, like to quantify how many grams do we have of something, or how many, how many atoms do we have, or how many. So basically, your stoichiometry is based balancing equations. That's all based on the particulate nature of matter. When we're talking about energy, we're going to be talking about the wave form of matter. Okay. And that's where your spectrums come into place, your spectra come. So to understand that, we first need to understand how does a wave work. Okay. So wave usually has two different properties. It has wavelength, okay, and it has frequency. Okay. So these are two properties of any wave in nature. Okay. So imagine this being an atom, but this atom is now behaving as a wave. Okay. As I said, the particulate nature and the wave nature. So the wave nature will have a wavelength and will have a frequency. Okay. Now, what is wavelength and what is frequency? Okay. So frequency is like, frequency is more described like the energy, that the magnitude of any wave. Okay. The magnitude of any wave. So if you want to feel, okay, the strength of a wave, you're going to look at frequency. Okay. Magnitude of any wave, or it's the strength, okay, of any wave. When you're talking about wavelength, you're talking about how far it can travel. Okay. So you're talking about the distances that it can cover. All right. So wavelength helps to identify the distance traveled by the wave. Okay. And based on the wavelength and frequency, then it's also possible to identify the energy. Okay. The energy. So these are three different properties that we need to understand to then get inside electronic configuration and understand then how does it work based on all of this. Okay. So the key point here is first to understand these two guys, these two properties, which then help then explain this one. Okay. Now, just by understanding this much, all right, that frequency is magnitude or the strength of the wave, and wavelength is how far a wave travels. Which do you think would so if you have high wavelength, would you have more energy, or if you have high frequency, you would have more energy?
If you have more frequency, you'd have more energy.
That's correct. That's correct. Okay. So high frequency, okay, because it's stronger, it would have more energy. Okay. So high frequency would have higher amount of energy. Okay. All right. So examples of waves. Let's before we actually show all of these types of any examples of waves, okay, or yeah, any examples of waves in nature that you know about, okay, that are very high in frequency, like they have a lot of strength. You can think about hospitals, some things that are used, some kind of rays or waves that are used in hospitals. What would
I
that
was
be?
thinking,
Yeah.
I was thinking more earthquakes.
Earthquakes. Okay, earthquakes. Earthquakes are a bit different. Think about
So maybe something to measure heart rates.
yeah. So what kind of so when you want to do when you want to look at the bone inside your body, what do you use? What kind of rays do you use to actually look at it? When a doctor is looking at the bones, how do they do that? What kind of rays do they pass
An
through?
X-ray.
X-rays, yeah, X-rays. Okay. Another one that they use a lot is gamma rays. This is used a lot in chemotherapy. Okay, gamma radiation is used a lot. Okay, gamma rays as well. Anything else? Something that's very
Um,
that the sun has that's very strong and causes us to burn if it's too hot.
ultraviolet radiation.
Yeah, UV rays. Okay, so these
Then
three. Yeah. Anyone? Any
what
more?
about microwaves?
Microwaves. Yes, microwaves as well. Okay.
Infrared.
Infrared is a little bit. Um, it's much higher in wavelength. Okay, not so much energy. Can travel far enough. That's why like in infrared is used for detection. It's used for detection of heat energy, right?
Yes.
Its energy is not very high. It's more higher on the wavelength side. So yeah, these four are mostly the kind of waves that you find are high in frequency. Okay. Then what about, so you said about then wavelengths, high wavelengths. Okay. So high wavelengths, which ones do you think? So you said we discussed about infrared already. Okay, that I'm going to tell you also how it looks like. Then what else? Any other waves you can think of? Actually,
Alpha.
microwaves are also very sorry. Microwaves don't go here. Infrared. It's actually microwaves are high in wavelength again, but they're very. That's why all of these waves, the high wavelength sites, they actually detect heat. They can provide heat, but then because heat is released very quickly. That's why they don't retain a lot of energy. Okay. What
Hmm.
others did you say? Which one did you say?
Radio wave.
Radio waves. Yes, radio waves can travel very large distances, right? That's why we can hear the FM station in Lisbon, in Setúbal, very easily. RFM or any other uh, radio channel. Tons of them, right? So yeah,
Yes.
these are the three main that have high wavelengths. And then in the middle of all of this, you have your visible region, all right, which is the region in which we can see. Okay, so that's a little bit in the middle. So anything on the left hand, so you have your Vibgyor over here. Why the colors of the rainbow? Violet, indigo, blue, green, yellow, orange, red. Okay, so exactly close to this side, you have your infrared. That's why it's next to red. Okay, infrared. And then exactly after your violet, you have your UV rays, your ultraviolet. Okay, that's why it's called ultraviolet rays. Okay, so you have your high wavelengths, your high frequencies. So where do you think the energy is going to be more? Which side is the energy going to be more?
Um, the right side.
Yeah, that's correct. Okay, so high energy is over here. So energy is going to be more over this side. Okay, and then on this side you have low energy, right?
Yes.
Okay, so that's basically the kind of different types of waves we know in nature that exist, and a little bit of classification of waves. Okay, so this is the electromagnetic spectrum. It helps to classify it helps to classify waves based on their wavelengths and frequencies. Okay, all right. So that's what the EM spectrum does. Okay. And if you want to look at it in terms of representation, let's look at that as well. So yeah, you're gonna have your radio waves. So the waves are gonna be fatter if you have a higher wavelength. Okay, they're gonna be fatter, and then they're gonna get thinner as the wavelength reduces. Okay, so this is gonna be more like radio waves. All right, then something over here in the middle over here would be your microwaves, which also have a high wavelength, and then your infrared, okay, and then your visible, right? And then it's going to get even more packed, all right? So you have your X-rays, sorry, you have your UV rays, X-rays, and then gamma rays, which are really, really. So gamma rays have the shortest wavelength. So that means that, if you need to have exposure to gamma rays, you need to be really, really close to them, right? Because they have a very small wavelength. Okay. Because if something has a very high frequency, it would have a very low wavelength. If something has a very high wavelength, it would have a very low frequency. Okay. So wavelength and frequency are inversely proportional to each other. Okay.
Isn't there a formula?
Yeah.
Isn't it frequency times wavelength equals to C,
Yeah.
speed of light?
Yes, yeah, that's more when we study Planck's constant and when we study Einstein's theory of relativity, then that's used a lot. But yes, that's the part where you have like something. It's more nuclear physics, but yeah, it's more modern physics. But yeah, that's exactly where it comes from. So yeah, your frequency is inversely proportional to, sorry, frequency is mu. It's called as mu. Okay. It's written like this. It's not a V, but it's written like this. And then your frequency can be written as 1 over F. Okay. All right. And for frequency, actually, the formula for frequency itself is 1 over T, where T is the number of seconds. Sorry, the number of revolutions. Okay. So yeah, that's inversely proportional. Um, and yeah, so your wavelength can be usually given as lambda. Sorry. So yeah, that's where you get the expression from. Mu lambda is equal to the speed of light. Okay, that's usually the case. So yeah, all of these waves, okay, all waves, all particles, they usually move with the speed of light. What's the speed of light? 3.0
3.00 times 10 to the power of 8.
meters per second, right?
Yes. And isn't there an Albert Einstein formula, which is formula for energy?
Yes, E is equal to mc squared.
Yes, yeah. Do I have to know that for chemistry?
Um, Not at this stage, okay? You have that, but I think that would be in radioactivity, not right now,
Okay.
okay? I think that you don't have it right now for sure. Right now, we're more concerned about electrons and their energies, and we want to understand more about what happens to electrons when they gain energy, when they lose energy, all that kind of stuff. Okay. In terms of, well, actually, you don't have it. No, you don't. You don't have nuclear physics anymore. Ah, because you're not. That's in physics. Your brother is gonna have that, not you. He's gonna
Okay.
have it, and he hates it, right? He hates chemistry, so that's gonna be fun.
Yes.
Yeah, he has nuclear physics, not you though. You don't have that because you have more than organic chemistry, which you seem to not like as well. That's gonna be
Yeah.
interesting. But yeah, you're gonna have equilibrium. I think you like equilibrium a lot because that's that's a physical chemistry chapter as well. Now now when we're gonna still like do a lot of inorganic chemistry. Like for the next 1 month, or even more than 1 month, we will do until December. We will do more of just inorganic chemistry. Okay. In fact, even till
Would
January. Yeah.
would you
Tell me.
say 50% of chemistry chill is organic chemistry?
Um, I would say mm, not 50%. I'd say it would be. It's kind of like about 30%, not more than 30%.
Okay.
Yeah, 30% would be organic. You'd have about 35% of inorganic, and then 35% of physical chemistry. Because you have a lot of physical chemistry. I would say, in fact, physical chemistry would be at 40%, in my opinion. So you'd have 40, 30, 30. That would be the ratio. I think so. Because there's a lot of chapters for physical chemistry that you have. You have a lot of material in all of equilibrium, unit 6, acids, bases. All of these are actually considered to be inorganic, but there's a lot of calculations over there. So it's a lot of inorganic with physical chemistry. Okay. Redox reactions. These are inorganic. You have and physical chemistry, electrochemical cells, electrolysis. All of this is physical chemistry. So for you, actually, it's not that bad because the only part you don't like that much is organic chemistry, right? And that is basically um, yeah, that is with hybridization, sigma pi bonds, resonance. Those are the topics that you have mostly that would be more um, in regards with all of this. So yeah, and then lone pairs, and of course how to localize lone pairs of electrons. Those are some of the things that you would have. um, I don't think you have very core organic chemistry as well, because the new IB syllabus, it's let me see. Yeah, you have models of bonding, which is ionic, covalent, metallic. This is all or inorganic. That's the next topic after we finish this. Then you have periodic table and functional group. Functional groups is the part that is of organic chemistry. So that's like probably just 5% of your syllabus. Then what drives chemical reactions? No, entropy, all of that is physical. Amounts of reaction, that's also physical. What are mechanisms? Yeah, this one, electron transfer, proton transfer, electron sharing reactions. This has some of organic chemistry. Actually, don't have that much organic chemistry. It's not that much. Yeah,
That's
that's
good.
yeah. You don't have that much. The new IB syllabus, you don't have that. In the old one, you had a lot of organic chemistry actually.
Mm,
Um, in this one, it doesn't seem more than actually doesn't seem more than 20% to me now that I have a look at it. 20, 25%, maybe even less. 20, 25%, yeah. So that's good. That's good. Okay. All right. So where we are. So is this clear? The part about where you why we're studying about. So first we have to understand what this. Okay. The question is why are we studying this? what is the relation with chemistry? So, as I said, when we're studying particles or we're studying atoms, we need to understand that matter can have both. It can be both, is both a particle and is also a wave. Okay, so we studied some of the particulate nature of matter, which was like moles, the stoichiometry, balancing equations, chemical mixtures, etc. All of that is related to the particulate nature. That's why it's called the particulate nature of matter. Now we're starting to study a little bit about the wave nature of matter, but it's not that much. It's only in relation with and with electrons and energy. So much so with electrons and energy. But this is just like a brief overview, okay, on all of that. Um, then types of spectrum. Okay, so you have continuous spectrums and you have line spectrums. Okay, continuous spectrums is like your rainbow. Okay, so like when you have a rainbow, it's going to be a continuous spectrum, right? You have all the Vibgyor colors. That's a continuous spectrum. A line spectrum, though, is more in relation with a single, it can be a single element or it can be a single compound. Okay. And the way how you see a line spectrum is like this. Okay. So a line spectrum would have just single frequency lines, okay, on them. Whereas in a continuous spectrum, these would all just be, say you have, these would all be intertwined together. Okay. These are all interconnected with each other. Okay. So this would be more like a continuous spectrum. Okay, because it continues. It continues, one spectrum continues into the next one, and then so on and so forth. Okay. In a line spectrum, you have single lines. Okay. And these represent single spectrums of an element, or it can be for a compound. Okay. This is a line spectrum. And this is what we're actually interested in, okay, for electronic configurations. Okay. This line spectrum is what is used um, scientifically to identify different electronic transitions from one energy level to another energy level. I'm going to explain in a little bit how that works. Okay. Explain that as well. So in line spectrums, you would usually have different colors. Okay, so they say this one is just red, then this one is yellow, and then the further you go, it becomes kind of bluish. Okay, bluish, darkish blue, violet, indigo, kind of those colors. Similarly like a continuous spectrum, but just very separate from each other. Okay, all right. So in your formula booklet, okay, though, frequency and wavelength, the relationship is given, okay, and you will also find the speed of light in there and other useful constants which we'll use later on, okay, not right now. But yeah, okay, one more thing. So a line spectrum, okay, it shows certain frequencies. The line spectrum, it tells us the light emitted from atoms, okay, at certain frequencies, at fixed frequencies, because these fixed frequencies have fixed amount of energies, okay, and these fixed amount of energy packets, these are all quanta. Energy packets of fixed energy are called quanta, and that's where the word quantum comes from, okay. So quantum is basically an energy packet, all right. Quantum computing, something that's something that's going to be used in the near future a lot. Quantum computing, it's based on energy packets, okay, based on energy transitions of different electrons. So we already do that, like with electricity, okay. Electricity is a form of transmitting energy packets from one place to another place, okay, because you're transmitting electrons with high energy from one place to another place, for example, okay. Similarly, you can have different applications, right? We haven't yet discussed. Oh, you don't. You're not in physics. Magnetic forces of energy. You don't have all of that. Good thing you don't have all of that. But but yeah, it's something that's used quite frequently. So the emission spectrum, then, okay. So this is what. So how do we get this? The important question is, how do we get this? What do you think would happen? Let's say this is my nucleus, okay, and this is electron revolving around this nucleus, okay. Now there's two situations that can happen, all right. Either this electron can gain energy or it can lose energy, okay. So let's see what would happen in either situation, okay. In this case, you have the nucleus. The electron actually, can I draw this again a little bit smaller? So you have the nucleus, and then you have the electron quite close to the nucleus, okay? And then over here, you have the nucleus, and then you have the electron a bit further away, okay? All right, from the nucleus. So when an electron gains energy, okay, when there's energy absorption, okay, energy absorption is gaining energy. It's going to move from a lower energy state to a higher energy state. And when it moves into a higher energy state, it basically goes further away from the nucleus. Okay. In the opposite scenario, if there is an atom with electron that is already in a higher energy state and it releases some energy in the form of heat or light or any other form, then it's going to go into a lower energy state and it's going to come closer to the electron. And this is called energy emission. Okay.
So wait, if the electron gains energy, it will go further away from the nucleus.
Yes. Yes.
Okay.
Okay. And that's why you have the shells. We will discuss about the shells in a little bit. Okay. Which is something that's called the principal quantum number. We'll discuss about that in a little bit. But so this place where the electron is stable, happy, and it is, it's imagine being a person who's happy and content with whatever he has. Okay. That's called the ground state. Okay. Happy and content with what the guy has. Okay. That's the ground state. And so imagine suddenly you become rich. What's going to happen? You're going to go party and your energy is going to go really high for a little bit, right?
Yes.
Yes. So you were happy and you were okay when you didn't have a lot of money. That's the ground state. Not a lot of money. And then you receive a lot of money at a single time. Imagine you win the lottery. You win the Euro millions and you win 72 million euros in one shot. So now you're super rich. Now you can do whatever you want. You don't want to study. Don't want to do. You just want to go and party, and and your energy is going to suddenly go really high. That's what you call the excited state.
Okay.
Okay. So you're excited. You want to just show the world, man, you're the guy. You have the money. You have the dough. You can do whatever you, right? And that's going to last for some time. You're going to go, you're going to party, you're going to spend a lot of money. But, there's going to come a certain point where you're like, oh man, I don't think I can do this anymore. So what's going to happen is you're going to return back to the ground state by releasing all the energy. That's exactly what the electron receives a lot of money in the form of energy. It gets excited. goes from the ground state to the excited state, and then it parties for some time, tries to get away from the nucleus, and then it realizes, hey, you know what? There's more to life than this. I better get all my stuff together and go back to what I was doing, have a purpose in life. So I go back to my ground state. Okay. And I
Okay.
release that amount of energy. That's exactly what is emitting that energy. So electron is basically like life. If you get rich too fast, that's the same thing happens to the electron. It gets excited. Okay. If you win the lottery, if you get something that increases your dopamine really quickly, it's the same thing. So it's the story of our life, right? This is the story of our life.
And how does the electron get excited?
So the electron can be excited, can be stimulated by several ways. It can be excited by light. Okay, that's called the photoelectric effect. Say if you have a metal, okay, and you strike light on it, it's going to increase the energy of the electron, and the electron is going to go into an excited state, and then it's going to release that energy after some time, which is then called the photoelectric effect. So light can be one form. The other form is heat.
Okay.
Okay. If you heat up, if you heat up a solution or you heat up water, okay, it's going to start evaporating because the energy is very high. It's going to convert from a liquid to a gas. And what happens when you go from liquid to gas? The energy also increases. So that's what happens. The electron increases its energy, all right, and then releases that energy in the form of heat. Again, that's another form. It can be
Okay.
also electricity. Okay, you can give electric currents to a specific metal that is a conductor, and that's going to allow other electrons. So silver is the best conductor of electricity. It's used mostly in robotics. Okay, it's even better than copper, but it's more expensive, of course, but it's the better conductor of electricity. So silver gets excited by moving its energy. Its energy goes higher when electricity is given to it. Okay, so it can be any form of energy. Then there's magnetic energy. You can give magnetic energy that's created by electric fields and magnetic fields working together. So if there's motion and electricity is happening together, like a generator, okay, that generates magnetic fields. So magnetic fields can push the electron away from the nucleus, excite it, and then bring it back. Another form of excitation. Okay, all right. The last one, you can bombard another electron into this nucleus, nuclear energy. That is also another form of energy that you can use. Okay, so that would in fact break the nucleus even. All right, that would split the atom into different daughter atoms, but also affects the electrons. The chain reaction happens because of the electrons. Okay, all right. So yeah, a lot of different ways of exciting an electron. Okay, there's not a single one. Just like life. Okay, there's not just money. It can be a beautiful woman. It can be a fantastic. So it can become, if you become famous really quickly, that also can make you excited really quickly. Just like life. Okay, electron is just like life. Okay, matter is life. So it makes sense that matter also suffers the same consequences like us when it gets a lot of energy. All right, it can suffer. It can be excited for some time and then come back to its ground state and be happy, and then be excited again and then come back. So just like life. Okay, so if you know the story of a life, you can know that you can understand electric you can understand emission, absorption, okay, of energy from electron, ground state, excited state. Okay, so
Okay.
this line spectra is exactly what would happen when the electron of, say, of helium, hydrogen, or any element. In this case, it's helium. Okay, it would emit specific frequencies. When it emits this energy, it emits specific frequencies.
Isn't it hydrogen?
Yeah, also hydrogen. Hydrogen has even more. Okay, I'll send you the notes for hydrogen. It has like different series of spectrums. Okay, and that's depending on different excitation states. We haven't discussed orbitals yet, but when we discuss orbitals, you'll understand hydrogen much better. Okay. Um, yeah. For now, it's best that we don't do hydrogen immediately because I always prefer to teach you first how the orbitals work and then come to hydrogen. Okay. But for now, yeah, any line spectrum would be something like this. Okay. You would have just specific lines at specific frequencies. Okay. Emits specific frequencies. Okay. So when you emit energy because of electron transitions or energy changes, it's going to emit specific frequencies, and those frequencies would show up as a line spectrum. Okay, all right, clear.
Okay.
All right. So look, it's 7. I hope you'll enjoy today's lesson. It was just a brief introduction into what quantum, what electromagnetic spectrum is. And then in the next class, we'll discuss a lot more about the energy transitions and we look at some of these energy transitions. Okay. All right.
Okay.
Yeah, Pierre.
Okay.
All right.
Yes.
Okay. Don't forget,
Okay.
send me the images of your work or scan it or send it to me so that I can have a look and then we can see which questions we need to work on. I'll send you the math one today after
Yes.
finishing with your brother. Okay? All right.
Okay. Bye
Bye.
bye, sir. Bye.
Bye. Bye.